Brownian motion. The Brownian motion process or Wiener process is one of the most useful stochastic processes in applied probability theory. It originated in physics as a description of Brownian motion. This phenomenon, named after the English botanist Robert Brown, who discovered it. The motion exhibited by a small particle that is totally immersed in liquid or gas. A stochastic process x of t for all t greater than or equal to 0 is said to be a Brownian motion process if the following conditions are met. The first, x of 0 is 0. The second is x of t for t greater than or equal to 0 has a stationary and independent increment. And the third, for every t greater than or equal to 0, x of t is normally distributed with mean 0 and variance sigma t. Geometric Brownian motion. A geometric Brownian motion, also known as exponential Brownian motion, is a continuous time stochastic process in which the logarithm of the randomly varying quantity follows a Brownian motion with drift. It is an important example of a stochastic process satisfying a stochastic differential equation. In particular, it is used in mathematical finance to model stock prices in the Black-Scholes model. A stochastic process S of t is said to follow a geometric Brownian motion if it satisfies the following stochastic differential equation, where S of t is a Brownian motion and mu and sigma are constants. For an arbitrary initial value S0, a stochastic differential equation has the analytic solution. To arrive at this formula, we will divide the stochastic differential equation by St in order to have our choice random variable be on only one side. From there, we write the previous equation in integral form, assuming W0 equals to 0. Of course, derivative of S over S looks related to a derivation of natural log of S. With substituting the quadratic variation of a stochastic differential equation, simplifying and taking exponential, then multiplying both sides by S0, we can obtain the claimed solution. The solution S is a log normally distributed random variable with expected value S0 times exponential mu t and variance equals to S0 squared times exponential 2 times mu t times exponential sigma squared t minus 1. A stochastic process logarithm of S is related to the log return of the stock price in the Black-Scholes model. And we will have expected value of log of S equals to log of S0 plus product of mu minus sigma squared dt over 2. Pricing stock options. In situations which money is to be received or paid out in different time periods, we must take into account the time value of money. That is, to be given the amount V at time t in the future is not worth as much as being given V immediately. The reason for this is that if we were immediately given V, then it could be loaned out with interest and so be worth more than V at time t. To take this into account, we will suppose that time 0 value also called the present value, the amount V to be earned at time t, is V times exponential negative alpha t, where alpha is often called the discount factor. In economic terms, the assumption of the discount function exponential negative alpha t is equivalent to the assumption that we can earn interest at a continuously compounded rate of 100 alpha percent per unit time. We consider a simple model for pricing an option to purchase a stock at a future time at a fixed price. Suppose the present price of a stock is $100 per unit share, and suppose we know that after one time period it will be in present value dollars either $200 or $50. It should be noted that the prices at time 1 are their present value. If the discount factor is alpha, then the actual possible prices at time 1 are either 200 times e to the alpha or 50 times e to the alpha.